Okay, this lesson is going to be on the rates of change. Again, we're revisiting this now that we know all of our derivative shortcut rules. And so just a reminder, the average rate of change is the same as the slope of a secant line. So if I have a graph, some function, and say here's A and here's B, then if I look at the 2 points between them, or the 2 points that are at A and B, excuse me, and I connect those with a line, to the best of my ability, then I have drawn a secant line there, and the average rate of change is the slope of that secant line. And so if you think about what you need for the slope formula, you need x's and y's. So this point over here is b for an x value, and then its y value, we don't know what it is, so we'll just say f of b. And then this point over here is an x value of a, and we'll call its y value f of a. So if I do the slope formula with these 2 points, then I have f of b minus f of a over b minus a, and that is the slope of the line between those, and it is the average rate of change on this function. The instantaneous rate of change is a little bit more complicated, and it is the slope of the tangent line. It's also known as the derivative at that point. So if I have a function and I pick a point that I'm going to call C, then at that point I can't really do the slope like I normally could, because in order to do the slope formula you have to have 2 points. If I am drawing in a tangent line here, it will look something like this, and I will know that the instantaneous rate of change, the derivative, is positive because that is an uphill sloping line, but I can't know that exact number using that slope formula. So that's where the calculus comes in, and the fact that it's the derivative at that point. So if this green function is my f of x, then the slope of this line is the f prime of c, the derivative at c. And remember, that's not the line, that's the slope of the line. Okay, that's important to keep in mind. Okay, so example 1, we want to find the average rate of change, and we have a function on 0 to 6. So anytime they say average rate of change, you're thinking slope formula. So I'm going to do f of 6 minus f of 0 over 6 minus 0. Now I have to figure out what f of 6 and f of 0 are by plugging into f of x. So if I plug in 6, I have 1/2 times 6 squared minus 4, and that's going to be 14. Then I'm going to subtract f of 0. So if I plug in 0, I have 1/2 times 0 squared minus 4, so that's negative 4. And obviously 6 minus 0 is 6. So if I change this to add, then I have 18 over 6, which is 3. So the average rate of change for this is 3. For number 2, I'm going to use that same exact function, and I'm going to find the instantaneous rate of change of f at 3. And so the instantaneous rate of change is the derivative. So again, if we need to look at that f, it was 1/2 x squared minus 4. So I need to first find the derivative, and this is just an easy one with the power rule. So I will have x, because 2 times 1/2 is 1, and then the derivative of 4 is 0. So the derivative is x, and if I plug in 3, I just get 3. And so my instantaneous rate of change of f at 3 is 3, which means the slope is 3. It's a positive uphill tangent. So let's try another one. Instantaneous rate of change of g of x, this function here, at 1. So again, instantaneous rate of change means I'm finding the derivative. So I have 10x plus 3, a little bit more complicated than last time. Plug in 1. And so I get 10 out times 1 plus 3, and I get 13. So this one instantaneous rate of change at 1 is 13. It's a very steep line. Now, as we go along, finally I'm going to introduce some vocabulary to talk about some things. Differentiable and non-differentiable. Differentiable just means you can take the derivative. And sometimes we use this algebraically when we're looking at something, but a lot of times we use it graphically, and it means I can draw a valid tangent line at that point, one that would be something that I could find the slope of. Obviously vertical tangent lines are undefined, or some of those points we had multiple tangent lines that we could draw, so those wouldn't be differentiable, which I'm going to talk about in a second. So differentiable just means you can take the derivative. Try to remember that one. Now, not differentiable are all those places that we've been talking about that have problems. If a section is vertical, so if the graph has a vertical section, the tangent line would be vertical, and if the tangent line is vertical, its slope is undefined. So that derivative would be undefined. So that would not be differentiable. A hole, you can't draw a tangent line to something that's not there, so that's not differentiable. Again, a vertical asymptote, you can't draw a tangent line to something that's not there. A jump, again, you can't draw to either end. It's just one of those places that a tangent line is impossible to draw. Now, these two cases, a sharp corner we come up with a lot. So the graph's coming along at one slope and turns and is immediately another slope. And this corner is very sharp, so it's like jumping from a slope of -3 to a slope of 0 or something. That sharp corner is one of those places where I could draw multiple tangent lines, and so it doesn't have just one answer, it has multiple answers, so technically it's not differentiable because we need it to have one answer for what we're doing. A cusp is a word you may not have seen before, and it's kind of like a pointy place. I always think about in the caves, the stalactites and the stalagmites. It's something like that. That happens occasionally, but that has a name. It's a cusp, and it's another one of those places where you could draw multiple tangent lines, so you don't have one answer, and therefore it's not differentiable. So let's go through an example that might have a problem. So example 4 has it wants us to find the instantaneous rate of change of this function at 5. Well, if you think about this function, what's going on at 5? And if you think back to your asymptotes and things like that, this has a vertical asymptote at 5. If you want to look at the graph, it's your toolbox function 1 over x moved right 5. So it would look like this. And so anytime there's a vertical asymptote, if they ask you for the rate of change, it does not exist. And so I'm going to write a sentence. I'm going to say it does not exist because there is a vertical asymptote. At x equals 5. Get in the habit of explaining yourself if you have something that doesn't work, just to be used to it and get ready for exams. Okay, that concludes this review lesson.